nanotechnology for over 40 years. I worked in the aerospace business for 12 years and was doing nanotechnology without knowing it. Then in 1990, we just started official programs that involve nanotechnology. And ever since then, the growth of nanotechnology is exponential. So today we have two lectures. We have lectures today and tomorrow. Today will be very qualitative, and tomorrow we're going to be more quantitative. Okay, so the people that are not necessarily engineers and scientists can relax today, get ready for tomorrow, and vice versa. So how many in here are going to have computers a big part of their life in the future? Raise your hand. Well, probably everybody, right? So that's really good to know. And how many people here are more entrepreneurial and want to start a business someday? Okay, four of you. Okay, I'll have a proposition for you later. I need some help, and I think you guys can help me. I'll spell that out later. So today, let's talk about nanotechnology. And your cell phone is the most amazing example of nanotechnology you can imagine. Right now, the transistors in cell phones and the features are about 2 nanometers. How big is 2 nanometers? 20 hydrogen atoms in a row. So small that, of course, we need transmission electron microscope to see it. So our future is just going to get more and more crazy, especially with the advent of AI. I just had an amazing discussion with Professor Hornyak about AI and all the things that are happening next 10, 20 years, which you will experience fully. So let's try to get you excited about what is actually nanotechnology and how it can impact your life. And surprise, your body inside is nothing but nanotechnology. Nature's nanotechnology. All right, everything in your body is at the nanoscale. So you have to be ready for that as well. All right, we're going to, let me see. Yeah. For the title of this course is Emerging Technologies, of course, and nanotechnology in particular. I think other lecturers will talk about the other parts of the emerging technologies. We call them NBIC and then parentheses R. So nanotechnology, biotechnology, information technology, and the cognitive sciences. So you're saying, oh wow, what an interesting group of things. However, all of them come together in confluence in robotics. So when we make our robots in the future, are they going to have cognitive abilities? So physicists are working with neurologists. Neurologists are working with biochemists. Biochemists, of course, are working with computer programmers, computer people, all together. This is what nanotechnology is. You need all of that to work together. So here's another picture of this. You can see changing the societal fabric towards a new structure. And in my opinion, however, nano is very fundamental to all of them. Okay, fundamental to biotechnology. I just lost my sound. Hello, I'll just keep lecturing. So nanotechnology, oh, my voice sounds so different. Is fundamental to biotechnology. I just mentioned how enzymes in your body are 2 to 20 nanometers in diameter. COVID virus, 100 nanometers in diameter. The battle that happens in your body happens at the nanoscale. The battle between the virus and your immune system happens at the nanoscale. It's fundamental to information technology in the form of the materials that go into your cell phone, that go into your computer. Those are nanoscale ingredients, nanoscale components. And then, of course, we're talking about neurology. When AI is going to be more prominent in our lives, all of the simulations of the human brain are going to be made of nanomaterial. Quantum computing. How many of you heard about quantum computing? Okay, that's already here. How does it work? Does anyone know how it works? Well, we know the digital, right? 0 and 1, 0 and 1, 1 and 0. But quantum computing doesn't deal with that anymore. Quantum computing deals with superpositions. So you can have 0, 1, and then superimpose 1, 1, 0, whatever. All of these things are increase your capability unlimited. So it's very different from digital technology. And then, of course, robotics. Robotics is I saw a video today of a robot playing ping pong. Is that real? Is it real or is it a simulation? I don't know. The fact that I don't know means it could be real. We don't know anymore what's real. Is it real or not? These are going to be societal issues that we have to deal with. So what is nano? Over the years, is it a separate academic discipline? It's a technology field. Is it a degree program? They offer at AIT, for example, they offer degrees in nanotechnology. At Chulalongkorn University, they have nanotechnology program, actually an incredible nanotechnology program right here on campus. I looked at their curriculum, quite fantastic. So we don't know exactly what it is. We know it's a billionth of a meter. That's what a nanoscale is. Nanometer is a billionth of a meter. But we don't know. We don't know what it is. We know it's disruptive. We know it's multidisciplinary. I told you about how many different fields would come together and work. Is it revolutionary? Absolutely. Is it disruptive? You answer that question. Is it disruptive? How many in here have cell phones? Okay, who doesn't have a cell phone? I'll give you 100 bucks. I saved 100 bucks. Yeah. Okay, everyone give me your cell phones and you live your life for 1 week without your cell phone. Can't. Change your life, it's disruptive. You have the information of the entire world at your fingertips. That's unbelievable. Dr. Punjak, could I get some water? Yes. Sorry, I forgot to tell you. But anyway, so we'll try to figure out what it is as we go through it. This is just a picture of a virus. Inside is either RNA or DNA. On the outside, you have these spikes. This looks like the COVID virus very much. And these spikes are what they're changing every time. When the thing is mutating into some kind of different form, these spikes are attacked by the immune system. And if the immune system can't fight it, which is viruses are very difficult to fight, then it enters the cell and then reproduces and releases more virus. DNA and RNA are nanoscale. DNA is about 2 nanometers wide, but in your cell it can be 2 meters high if you unwrap it. That's kind of amazing right there. So anyway, here's just a general virus, and these are absolutely nanoscale components. Quantum computing, right now we're doing it at very, very cold temperatures, but it's actually happening inside at the nanoscale. And they have worked out, there's I think Bell's criteria, I can't remember exactly the name of it, which
kind of gauges the amount of error that's produced by a computing system. And I think it's finally gotten over the threshold that it can be now usable. You can go to cloud and use it. It's actually available right now, from my understanding. Quantum computing is coming. Entropy, the brain, and it turns out that the people studying the brain and studying computers, this is the beauty of it. Equations are convergent. Equations are convergent. They have the same kind of equation. And they were independently derived. That's the biggest beauty of science, is when equations converge, you can make a unified theory. So you have the same kind of statistical, S is entropy, K is the Boltzmann constant, and ln omega is simply the amount of statistical distribution you have. So the emergent property for these ants, for example, ants have very few chemical programs, but taken together, they can form new behaviors. These ants here are excluding this ant. No one ever taught them to do that, it just happened. But anyway, these are things that happen at that's why we need to know our cognitive science, because when we put a brain inside of a robot, we better be sure we know what it does. Is it going to claim that it's a living thing? It's called sentience, right? But the robot actually will recognize its own existence. That's coming. It's coming. Neuroscience AI. These 6 things together seem unrelated, but they're called linguistics simply language. So artificial intelligence is going to use language. Are these instruments going to have philosophy to them, or are they going to have psychology? Okay, sorry about that. So we have to look at creation of a synthetic human brain, and that's going to be part of the emerging technologies. Right now, there's a program called Connectomics. Connect, so you know, connect. Atomics is a program made to map the human brain. How many connections do we have in our brain? We have about 100 billion cells, and we have over 1 trillion connections. How do you do that? Well, so far they've managed to map the brain of a little fruit fly, which has some 200,000 connections, right? It's a very simple creature. But what happens when they do that? Then they'll know exactly what's going on in your brain. Some of it is scary, some of it is fantastic, but it's happening, it's coming. So all of these things together, we need to know them, because when we're programming AI, not me, but you guys, we have to know what that thing is going to do. Will it have emotion? How many here have watched Star Trek? Remember the show Star Trek? The Next Generation with the Data, the character called Data, who was android, but he wanted to be more human, but he had no emotions. That can happen. Maybe 10, 20 years. So these are things that are all being enabled by nanotechnology. There's some robotics, some pictures. And here, are you nano ready? Now, I'm not asking you to become nanotechnologists. I'm just asking you to be aware of it. You know, how important it will be in your life. How many maybe here plan to go for Ph.D.? A few people, nobody. Mainly business people. You want to start a business. That's also very important. How much nanotechnology do you need to know? And you'll be amazed how much technology is coming from nanotechnology today. Globally, trillions of dollars GDP. So it's here. And it's been here already for quite a while. So what is nano? Just a brief definition, 1/1000th of a meter. That's what we're most interested in, is the size scale itself. And it just comes from the Greek root, nanos. These are just some examples of synthetic versus natural nanomaterials. And you can see the micron size, the millimeter is the ant, the dust mite, which is a very small creature, 200 microns. It's already very hard to see. The human hair, 10 to 50 microns. We can see that still, barely, but it's still, we can see. When it gets smaller, there's DNA, red blood cells are 2 to 5 microns. And then, of course, DNA is about 2 to 12 nanometers, depending on how it's coiled. On the other side of the ledger, MEMS, microelectromechanical systems, ancient technology. We've had that since before the 80s. There's a process of lithography that they can carve out these materials with lights, with different kinds of wavelengths. And also we can move atoms. This is a scanning tunneling microscope, able to pick up an atom and put it in a circle. And we call it the quantum corral. And then, of course, down here, we have carbon nanotube. Tomorrow, hopefully, we have a little project making one. But anyway, this is a few nanometers in diameter. I mean, maybe 1 nanometer in diameter. But it's turning out to be one of the most amazing materials. So this is, oh, here we go. We just kicked in. So this is the official definition. I'll let you read it later. But basically, just remember, officially, 1 to 100 nanometers in diameters. If you're writing a proposal, you want money from the government, they want you to stay within this boundary here. And the next highlighted, novel and differentiating properties. I'll just tell you one, that gold is red at the nanoscale. It's not gold color anymore. So things happen when things go to the nanoscale. So it's all about size. I mean, it's simply a technology based on size. That's all it is. A very small size to be accurate. So nano gold is red. Metals can become semiconductors. They have much lower melting points. The materials become very pure because impurities want to migrate to the surface of the nanoparticle to stabilize it. Small forces are important. Ballistic electrical conduction. If you can make a carbon nanotube kind of very long and perfect, it'll conduct electricity like a superconductor. It's actually more practical because it happens at room temperature. The reason being is simple. It's the mean free path of the electron is very long in a carbon nanotube, whereas in copper, which is one of our best conductors, it's still just a few nanometers, 20, 30, 40 nanometers, before it collides with a defect or another electron or something. That's why you get resistance in copper. So this would be resistance-free electrical conduction without eliminating any heat. That would save a lot of energy. Anyway, strongest materials, of course, catalysts are nanomaterials. The catalyst in your, how many here drive your car? You have cars. You have a catalytic converter. You know how it works? Anybody know how your catalytic converter works? You drive every day. It's filled with nanoparticles of metal, some kind of metal. And that metal is the one that converts exhaust gases into CO2 and whatever, which is also not a great gas. But that's what happens in your catalytic converter. Otherwise, the pollution would be really bad. Big cities, of course, have a problem. And of course, high collective surface area in your catalytic converter, because you have nanoparticles and many of them, your surface area is incredibly high. So just some good definitions. If you're in an elevator, someone comes up to you and says, "Hey, do you know the definition of nanotechnology?" course, that probably won't happen, but materials with at least one dimension along the nanoscale. Nanoscience is the study of nature's nanomaterials. Nanoscience is the study of nature's nanotechnology. And nanotechnology is the application of nanoscience for the purposes of industry and commerce. Okay, so technology is like any other technology. We use that technology in our society to do things. So just remember these pictures. We say that nanotechnology is horizontal. Nanoscience, again, we try to define it. It cuts across many, many different kinds of sciences, like, for example, environmental science, physics, biochemistry, biology, computer science, geology, medical, biomedical, chemistry. See, the nano from every single computer science. Of course, you have industrial sectors, construction, food and packaging, aerospace and defense. Who were the first people over nanoscience? In the US was the military organizations. They were the first people that said, hey, this is important. We're going to have to take advantage. A lot of them, everything they make has nanotechnology materials in it. For healthcare, there's new drugs that deliver the drug directly to the cancer, not affecting the other parts of your body. Things like that. Energy, of course, the solar cells are just phenomenal, going up to 50% efficiency. And then, of course, all the materials can be made nanoscale. So we can say that nanotechnology is horizontal, it's convergent, divergent, and emergent. There's chemistry, and then there's, so I have three voices here today, my voice, this intermediate voice, and then so that's interesting, okay. So horizontal, convergent, divergent, emergent. There's chemistry, and there's also nanochemistry. There's physics, there's nanophysics. There's biochemistry, there's nanobiochemistry. So interdisciplinary, you all know, but transdisciplinary is actually what BASI is made of. It's just beyond the regular kind of class that you probably took in high school. And then supradisciplinary, which has basically no boundaries. And I would almost say a lot of what goes on here is supradisciplinary. In other words, it's a lot of things, and we leave it up to students to sort them out as they wish. Kind of interesting. It's also enabling. Adding nanomaterials to products makes them better. We had, when we first taught this class, I think back in 2020, we had the students go into groups of 5 and create a nano business with a business plan. And you would be, I have some examples if you ever want to see them. Fantastic, brilliant. Some made masks, others made other kinds of products, but all based on nanotechnology. It's disruptive. We mentioned that just the cell phone is the best example. And it's revolutionary. It's just like another industrial revolution. And this is looking at all of the emerging technologies. Without a doubt, please also always be aware, and this is the hardest thing to do because you have a job, you do your job, you have your company, you do your work, is how does it affect a society? What does nanotechnology, what do we have to be worried about nanotechnology impact? Will there be job equity? I personally don't think it's going to make a difference, except that it's more amazing technology. Because I think those kind of issues are handled politically in different other ways. But nonetheless, I'll give you copies of all the presentations. Don't worry about it. So business, academia, government, all of these things are, of course, going to impact nanotechnology. But for some reason, governments around the world, and Thailand included, making sure that we stay ahead of the technology. So there's a lot of programs around Thailand, for example, that are nanotechnology programs, even at the government level. Nanotech, how many of you guys are familiar with Science Park? You may get a job there someday, but they have one institution called Nanotech, Nemtech, Biotech, Amtech. Incredible amount of nano going on there, a lot of papers being written. So this is, we're back, I just have to pause it. So this is looking at our industrial revolutions. Here's a gold 55 cluster. It's not a bad picture of it, but I want a better one. And right now, nanoparticles, nanomachines are coming. So a lot of them are already here. So be ready for that. Is it the fourth industrial revolution, the big industrial revolution? Okay, now let's go to the next slide. And do this. Okay, first thing I'll do is quit here. Come on, quit. Okay, I need assistance. Okay, I want to load my next slide. One of these PCs are just a curse. I like them. Okay, number 2. Okay. Oh, now we have to make it big. Hey, how do we do that? Down here? This one? Hello. How about this one? Oh, did it. It's pure luck. Okay, let's move on to the next presentation. All right. So I'm blowing the horn of nanotechnology. Obviously, I've been in it for a long time, and I've never ceased to be amazed about the latest developments that are happening. So I have enthusiasm for this, and I want everyone to know about it. So the next thing we want to talk is about nanomaterials at the interface. What does that mean? We have continuums. For example, we understand the space-time continuum, right? And we understand the electromagnetic continuum. It's like a smooth progression from one wavelength to the next, even though the extremities can be very different, right? That's a continuum. Time just marches on, it's a continuum, evenly, but it goes faster when you get older. So what is the continuum of size? That's one thing we'll look at. In other words, from the planet Jupiter down to planet Earth, to a tennis ball, to atoms, molecules, and subatomic particles, right? That's a kind of a continuum of size. What we're claiming is that nanomaterials are at the continuum, at the interface between bulk materials and atoms and molecules. No other material can say that. We can say micron materials are at the interface between bulk materials and nanomaterials, but that doesn't matter because bulk materials and micron materials are bulk materials. In other words, they have the same material properties. So we have a continuum of physical and chemical properties, continuum of structure and function, continuum of living things, right? Throughout our living history, there's been living things that are our ancestors, it goes back farther. The continuum of chemical bonding, many kinds of chemical bonding. The interface between living and non-living things, the interface between natural and synthetic nanomaterials, and let me just give some examples. So here we look at the interface between bulk materials and the domain of atoms and molecules. Clear. There's a good picture of cuboctahedral gold. In the middle, there's a atomic force microscope image of a porous aluminum membrane. The diameter of the pores are about 50 nanometers. 50 nanometers. That's the kind of picture we can make of it. And to the left, just an example of a carbon nanotube. Again, a few nanometers in diameter, but can be extremely long. So micromaterials are bulk because their physical properties are still the same as bulk. In other words, a micron-sized gold particle will melt at the same temperature as a big gold chunk of gold. So we say nanomaterials are special in that way. And this is just for your information, we can go less than number of atoms, 2 to 20, the diameter less than 1.1 nanometer. The surface to volume ratio, we're going to talk about that tomorrow in great detail. Doesn't matter, it's so small it doesn't matter. And then you have the small size, the 20 to 500 atoms, but up to now 3 nanometers in size. And then the largest, just gigantic materials. It can be 100 nanometer like a virus. And surface to volume ratio is going down as we get larger and larger. Okay, continuum of chemical and physical properties. And this is a corollary of size. As particles get smaller, they become more quantum in their behavior. Now, quantum mechanics is just simply put as possible. They have discrete behaviors rather than continuous behaviors. It's just like an electron transition, just goes from here to here, nothing in between. So anyway, you can look at the different kinds of theories. You have the quantum molecular orbital stuff over there, which is basic Schrödinger equation. In the middle, we have what's called Hokoluko, which is cluster orbitals. So we can actually define orbitals of 55 atoms that are clustered together. And then, of course, classical band theory in physics. If you guys are computers, I'm sure you've heard about band theory. That's how your computers work, especially in the silicon world, semiconductor world. Okay? So anyway, you can see that there's another transition here. Here, this is nanomaterials at the structure function. This is an interesting question. Professor Poonjai and I, we've talked about what is this called telos. And what does that mean? That there's a purpose, that something does something. This is an ancient argument, long time ago. Why are we here? Do we have a purpose to be here? Or do we just happen due to random events, chemical events? You can resolve that for yourselves. But anyway, at the interface, we have what's called a stochastic domain, where things just react statistically, you want to say. And we look at water and hydrogen, formed from hydrogen and oxygen, et cetera, et cetera. And then on this side, you have deliberate structures that actually do something, that have this, in quotations, a purpose, right? So the whole idea of photosynthesis, there's a lot of components to photosynthesis. And they serve to do what? They take carbon dioxide, fix it, make sugar, and they give that sugar to us, and we make carbon dioxide. So is there a purpose to all of this? This is where the philosophy becomes really important in the cognitive science. You start talking about stuff like this. So right at the interface, there are things that are technically not living, but they have structure and function. And there are molecules, there are two kinds of molecules here. One is a protein structure. This is valinomycin, and all it does, it transports potassium into the cell. That's all it does. But it's just a molecule, it's just a molecular reaction, okay? Whereas the next step up is something called the K channel, where potassium is actually selectively drawn into it. You can see it, probably thousands of atoms. So this definitely has structure and function. This is on the verge of structure and function. So at the nano domain, you have this whole area of, this is where structure and function start working together.
Nanoengineering happening on the right hand side?
Nanoengineering is definitely structure and function, absolutely. Because engineering by definition is making something to do something. There's only two things that have structure and function relationships: living things and man-made things. That's it, nothing else. A mountain doesn't have structure and function. It's a mountain pushed up by magma, collects rainwater. I mean, those are stochastic events, but they don't have structure and function relationship. You can't say the sun has a purpose, do you? Can you? Yeah, it gives us light, but that's not its purpose. It lights the whole solar system. You happen to use that light. Anyway, this is good philosophical arguments we can discuss at a cafe. So valinomycin, again, is just showing you how valinomycin works. I don't have to dwell on that too much. But it's a molecule that the purple object is a potassium cation, and it changes its configuration from water soluble to not soluble, and that makes it go through the membrane. And then it gives it up. So the K channel, again, this is another picture. There's a selectivity, good heavens. There's a selectivity filters, all kinds of size exclusion. And it's a very, very complicated protein structure. That is, this is the cell membrane. This is a big oily hydrocarbon chain. These are water-soluble type components, right? Either side. Definite structure and function. Okay, the continuum of living things. I don't want to dwell too much on this because we're not, but living and non-living things. The smallest living things are nanoscale. There's some bacteria that are about 250 nanometers in diameter, the smallest bacteria. And the viruses can be anywhere from 100 to 10 nanometers in diameter. But then you have nanomaterials that are not living, like DNA technically is not living. Although some people make that argument. Why does DNA want to reproduce itself? That's the whole key to all of this. You're here because of your DNA. Your name. Bob. I'm going to call you DNA Bob because your DNA. There's something about DNA that says, God, we got to make more of them. I don't think anyone has the answer yet. A lot of good research papers on it, but nobody knows for sure. What is driving DNA? Ultimately, entropy is, we understand that. The living things increase the entropy of the universe, and that's one reason why we thrive like we do. But why DNA? I don't know. DNA wants to, but it's technically, some people don't think viruses are living. I do. They're just a protein shell around the DNA or RNA. That's all they are. Nothing more. But sorry, is this being recorded? Oh, you can edit, right? But they want to reproduce. It's at the nanoscale. I don't know what's going on. Anyway, you can see the pictures and the larger living things we know. Chemical energy, there's all kinds of chemical bonds. Nanomaterials hold no special place there because everything can do these bonds, big and little. But anyway, all of them do affect nanomaterials too. Now, this is what's really interesting. The interface between inorganic and biomolecular worlds. Carbon fixation by plants is done by enzymes. The enzyme is at the nanoscale. So all of life is dependent on the enzyme that fixes carbon. I mean, let's say 99%, there's some lives that don't depend on carbon. Nitrogen fixation, also done by enzymes. Right here, here's some pictures of some enzymes. So on this side, we have actually the most stable kind of molecules, CO2, O2, N2, H2, all of these molecules are very stable. And these are products, these kind of sugars, different kinds of proteins, all amino acids. So the thing that converts those things, which are hydrogen, oxygen, nitrogen, extremely stable chemicals, very strongly stable chemicals, converts them into usable biochemical materials. It happens at the nanoscale. So there's a special place for nanomaterials there. And of course, what's most important to medical researchers and industry is that nanomaterials are at the interface between synthetic and natural domain. Here, the rose petal lotus surface in the flowers and why is a rose petal always so fresh, right? Did you ever wonder? How many here have girlfriends? Everybody? Nobody has a girlfriend? Well, I can tell you why. You don't understand the rose petal effect. You ask a lady out to a date, bring some roses and say, the rose petal effect is because the surface of the rose is nanoscale. Right? She knows. She's waiting. Okay. Nanoscale. It traps the water onto the surface of the rose. So it always has this fresh, always fresh.
What do you like to say that, students here that take high school chemistry?
Yeah, okay.
So chemical equation is a little bit like compound.
Yeah,
I
exactly.
have so many molecules of sugar, water here, hydrogen here, nothing sugar you can. But the mechanism, the geometry of it, if you want to understand that's that we're not science.
Well, like I said, it's about materials and size. So there's something about its size that, and of course its chemical nature, that is allow it to trap water. I'll show you a picture of these structures in a minute. You know the lotus leaf here in Thailand, yeah? The lotus leaf, did you ever play with the water on the lotus leaf as a kid? What happens? Did you ever say, God, I wonder if there's any nanotechnology involved when we were 10 years old? No. It's nano and micro technology that has these little mountains, little peaks all along the surface of the lotus leaf. When you reduce the area of the contact to the water, you reduce the surface energy, okay? And it simply will roll around. If it's flat, there's something called the water contact angle. If I put a drop of water on gold, the water or glass, the water will spread out, right? We may talk about that in a little bit. There's so much incredible science, right? But if I put it on Teflon, it beads up a little bit like this. But if I put it on a lotus leaf, it's almost perfectly round. And that's because the surface is micro nanostructured. And it doesn't allow the surface of the water, there's not enough energy to overcome the surface tension of water. So there's two things. There is a chemical component because you may want to attract the water, but secondly, you don't want to dissolve it. And that's because just the shape. So that's the rose petal effect. So guys, don't forget next time. Say, look, hey, I got a rose here. You like it? I'll tell you why it's so fresh. Okay. That's also, I can also say the same thing about diamonds. Okay. Graphite is 4 kilojoules per mole, 4 kilojoules per mole, more stable than diamond. Okay. So why would you buy diamonds? Tell your girlfriend, I got you some graphite. It's 4 kilojoules per mole. Diamond is eventually going to turn into it. So why should I waste my money on a diamond? Right? Agree. Everyone agrees. Okay. Okay, so you look at all of these different dye-sensitized solar cells. These are things we make and we learn from our natural counterparts. For example, the dye-sensitized solar cell is based on photosynthesis. Many things. So here nano is at the interface of these worlds. Okay, I claim nanomaterials live on the curve. What I mean by that is all their properties are either like this, or like this, or like this, or like this. Either steeply increasing or decreasing or exponential or hyperbolic, whatever you want to call it. So if I get, remember, bulk material properties are very boring. Melting point of gold, melting point of gold, melting point of gold, watching my cord. And then at about 100 nanometers, it starts going down. And it goes all the way to 600. See, all of a sudden it's no longer like regular gold. It's very small. Exciton wavelength, heat of absorption, cohesion energy, particle magnetic moment, Kelvin pressure, nearest neighbor distances, all these things are extreme. So when you guys are familiar with MRI, right? Magnetic resonance is also very important in treating cancer. So what that happens is they take iron oxide particles and they target them with different kinds of what are called homing proteins. These proteins target the cancer cell. All right? They don't go anywhere else. They target only the cancer cell because there's certain chemicals on the surface of the cancer cell that only happen on cancer cells. So that once they attach themselves to the cancer cell, then you apply a magnetic field. Well, the paramagnetic material, like iron oxide, will start flipping its poles back and forth, depending on the frequency, right? And what happens then is heats. It's called high thermal heating of ablation of cancer. So it just kills the cancer cell by heat. But it's because of the iron oxide nanoparticle flipping its poles back and forth, that heats up things. So it heats it up 10 degrees more. Well, that would, if our whole body was heated up 10 degrees more, that would be finished. But however, if you do it to very locally at a cancer cell, no problem. Incredible technology. So these are but here's the thing. You'll notice that magnetic moment is it's too small. There is no magnetic moment per se. You have to have it right here on this side, which may be 7 nanometers. You want your particles 7 nanometers. The power of nano. Okay, so we have incredibly high surface area. Tomorrow we're going to have some fun with that. Surface to volume ratio, a very important parameter. Small components, incredibly long fibers, strong materials, fast enzymes, remarkable, all of these things. So incredibly high surface area, just to show you an example here. If I took a cube material, that's a lot of material, and I broke it up into 1 nanometer cubes. How much? Oh, yeah, sorry. I think the one good thing about this, it wakes everybody up really fast. So how much surface area do I have altogether? Okay, and what happened, you can see, all we're going to do in this class is algebra, all right? We're going to do tomorrow vector algebra, topological algebra, and just regular algebra. You all know algebra, so it turns out if I do the calculation, I get 6,000 square kilometers of area. How big is that? That's bigger than Bangkok. It's as big as the state of Delaware in the United States. Bigger, what province here we can have? It's just a big province, huge province, like half of Thailand, I think. No, yeah. Yeah, another example, the alveoli in your lung, which are the little balls that hold the air. If I spread those all out, it would be just the area of a tennis court. Absolutely true. Okay, so the length of DNA, I'm not going to worry about multiplying it by 30 trillion because that's how many cells you have. If I multiply anything by 30 trillion, I'm going to have a big number. But just remember, if I take the DNA out of DNA Bob's cell, it would be 2.5 meters high. That's a nanomaterial. That's this. Well, I'm about 70, about up here. Phenomenal. So here, this is going back to Pluto and back, but that's if you multiply by all the cells in your body, which is about 30 trillion, many, many cells. Transistors. Now here, this is already a few years old information, but if 20 trillion transistors are manufactured globally every second, okay, how long would it take to fill the volume of a 5 millimeter drop of water? If the transistors are cubes, right? With a side equal to 7 nanometers, right? And please always check my math. I mean, I think I'm okay, but you know, one never knows. You guys are brilliant. So it takes about 8.5 days to just to fill the volume of a drop of water. That's a phenomenal amount. So if that in 1 year, 216 milliliters of transistors are produced, which is a pile of dust in your hand. That bottle is how many milliliters? 500? Or 600? Okay, that's half of that. That's all the transistors in a year that are going into your computers. That's if they're 7 nanometers, which is what they are mostly today still, even though there's much smaller. Enzyme turnover, don't worry about the numbers, but when enzyme can turn over 560,000 substrates every second, we can't comprehend that. How do you, I can't even comprehend 100%. So this is an enzyme called catalase, which is the fastest of enzymes, and it works on hydrogen peroxide, but that's fast. And there's a lot of them, so there's high collective surface area too. There's even some enzymes that do 1 million per minute. Strongest materials, of course, carbon nanotubes. If I just measure the bond strength here and use that in my calculation, and by the way, you can see it's a tube made purely of carbon, and for some reason it becomes incredibly strong that way. Actually, graphite is very strong this way. So you can just take this tube and wrap it around and you have a carbon nanotube. We can call this a sheet of graphene, one two-dimensional sheet of carbon, honeycomb carbon. So we take that. Again, please, it's just algebra. We use a force constant, 1/2 kx squared, right? We know that from basic physics. And how do we figure out the energy? And please just go through it yourself. It's really a good exercise to do, okay? And we find out at the end of all of this that, by the way, our goal, I'm sorry, I forgot to tell you the goal. We want to pick up the Empire State Building in New York. So I'm asking you, using a certain kind of carbon nanotube, how many of them do I need to pick up the Empire State Building in New York? Well, the Empire State Building is 365,000 tons. My Thai remedy for coughing is the best in the world. Excuse me, it's in my bag upstairs. I should have brought it down. But so the Empire State Building, that's a huge building. How do we pick it up? Well, after doing all the calculations, and then we figure out what kind of cable, there's distances, of course, between the, and I have this problem coming up again, I think. 15 centimeters. How much is that? Not too much. So anyway, you can see some of the strongest materials. How many of you here have heard about the space elevator project? Some people dream about that. I think it will be a dream for a long time. But what they do is they buoy something in the ocean. And then they put this thing into geosynchronous orbit. So it stays with the Earth wherever it goes. And I mean, it has, what is geosync, 35,000 kilometers? I can't remember what exactly. It's a long way up there. But the only material that's strong enough is to make cables of carbon nanotubes. That will happen someday, the cables. I'm not sure about the space elevator. That we were, when I was in the United States, we were actually contacted by a company called Lift Group. They wanted us to work on the space elevator project with them. But I had some other things to do, so I couldn't do it. But there's some serious, the Japanese are working on it. They want to make an elevator to ours. It would be wonderful. You don't need big rockets, you just kind of, carbon nanotubes conduct electricity, so you can just ride up that thing. How many would go on that? How many here would go on there with me? Dr. Punjab. Okay, your name? Vic? Okay, Vic and I, Dr. Punjab, we're on there. Okay, I'll call you when we're ready. But anyway, that's strongest materials, incredibly strong materials. Stronger than steel. And it's 6 times stronger than tensile strength of steel divided by 1/6 the mass. So it's lighter but stronger. That's carbon nanotubes.
Silly question. So you talk about one how, bracket, things like
Oh, yeah, yeah.
that. If basically you have enough fiber.
Yeah.
And if you just throw a sprinkle, you know, just randomly throw in carbon nanotube, that automatically makes it stronger or says something more.
You mean just put them in randomly?
Yeah.
Yeah, that would make it even randomly because that would cover all the cancers, right? Wouldn't you think? I'm not expert at it, but that's what you can also direct them to be a certain direction. Like if I want to make something strong this way, impact resistant, I would want the carbon nanotubes this way. If I want to make, by the way, in Thailand and other places, the military is always doing research on bulletproof vest, right? I'll tell you a quick story about silk. Silk is a nanomaterial. Basically, the fibers of silk are nanoscale. So a long time ago, then they weave these fibers together and whatever. The Mongols used silk shirts, and the Chinese, I believe, and then they put their armor on top of that. But the silk shirt could stop an arrow. Because what happens is the arrow is flying like this. And then when the arrow hits the silk will wrap itself around the arrow and stop it. Carbon nanotube, think about that, is even at a smaller scale. If I'm a carbon nanotube, the tip of the arrow would look like this. This is the curvature of the tip. I can stop that arrow, no problem. So the next generation of these bulletproof vests, an incredible amount of nanotechnology inside. So that's where military, that's good all for protecting, right? Okay, so there's some pictures of advanced materials. These are micro electromechanical systems. The latest is, of course, nano electromechanical systems. And these are ancient pictures of over 20 years old from Sandia Lab and some other laboratories. And where do you see MEMS? It's in that projector. There are thousands of little reflectors inside that projector. And when you see a projector go bad, you'll see thousands of little dots on the screen. So that's what happened. You have to replace it. But it's in there. MEMS devices in your automobiles. How does your airbag work? The actuator for your airbag is a nanomaterial, a nano device. Pardon me, not a nano, MEMS device. Why? Because we know things happen faster when it's smaller. Who here wants your airbag to work quickly? Anybody? Everybody? No, you don't want your airbag to why? Okay, we'll talk about that later. But you want your airbag to work very quickly. So it has to be a MEMS device. it reacts immediately. Okay, this is a picture of a dust mite on top of some MEMS device. What time do we have? Do we show? Okay, we have two more hours. We only went 1 hour. Oh, I'm going too fast. Okay, I'm going too fast. Okay. All right, we'll have time. Okay, this is two different pictures of the same thing. One is an atomic force microscope, and this one was done with a scanning electron microscope. You have both of them on campus, and if you're interested in nanotechnology, go see these departments and watch them work these machines. It's just, when I first saw my first, I worked with the porous aluminum oxides. So when I first saw them under the transmission electron microscope, I couldn't believe it. It's like a whole new world. It looked like a starry sky, with millions of little lights coming through the holes. Unbelievable. So anyway, this is, you can see the scale bar here, it's 100 nanometers. Pores are roughly 100 nanometers diameter. Many uses: air filtration, gas separation, electro fuel cells, all kinds of different applications for these kinds of membranes. And then this is actually what I worked on when I was in aerospace, not knowing I was actually doing nanotechnology at the time. A lot of aluminum components were anodized, and even motorcycle components. A lot of the aluminum components are anodized to prevent corrosion. But during this anodized process, this porous system is formed. We wrote papers on why and all that. We figured out pretty much what's going on. But this is a nanoscale phenomenon that's made very easily in the lab. Even at AIT, we did a lot of projects with porous. My PhD dissertation dealt with making these porous membranes and then electroplating gold inside the membranes. And what happened was I made gold of every color, from purple, green, blue, red, ruby red, yellow, you name it. And why? It depended on the size of the gold particle. This is just hard to understand. You have gold. And then once the particle gets smaller and the shape of the particle, you can make different colors. I went to Germany and I won a little award, presentation of all these beautiful colors. And there's a lot of good physics behind it. How many here are good computer guys that can program? All right, okay, I need to talk to you. We did the programs, we wrote the programs to model the optical properties of these gold nanoparticles. So here comes the light. Just turn this sideways, okay? You got to go. Some were very long, some were spherical, some were flat, some were big this way, some were smaller this way. Okay? All of them were different colors. I'll bring it tomorrow. I'll remember to bring it tomorrow. So we modeled them. So we did the physics of it and we did the chemistry of it. It was the most wonderful dissertation because everything went well. Usually you have to suffer for a long time before you finally get something good. No, this thing worked out. It's great. Oh, God, thank you. Got out of there. But anyway, this is just part of nanotechnology. This membrane, it's optically transparent. Actually, these are colorized images, and of course, scanning electron microscope, you can't see through things. You reflect off the surface. But you can see this. That's just an amazing picture. It's just amazing. This is at the nanoscale. First got me really excited. So carbon nanotubes. This is one carbon nanotube here. These are what's called a multi-walled carbon nanotube. This is a transmission electron microscope. The distance between these two is 0.34 angstrom. Okay, very close. 3 angstrom. My gosh, very small. I can't remember. But anyway, you can see how just incredibly atomic this all is. Just perfect layers. And then the inner diameter, right? So we've got a lot of things planned. I am going to fund someday a project to make long nanotubes. I'm still going to do that. We went to Italy and entered a contest there for new technology. And the person, we got second place, okay? The person told us, said, your project is fantastic, but we had to give it to someone who would turn it into economic stuff right away. Okay, great. But we have a chance. You gotta, by the way, go to conferences, even when you're here, just go for a week somewhere, go to a conference. Your whole life will change, I guarantee you. I went to Europe during my Ph.D. And during that time, I met 30 professors. And by the way, if you go into academia, no matter where you go, they'll put you up, even here. Thank you, Dr. Puch, I appreciate it. But you're an academic, you're going to give a talk, a lecture, whatever. They put you up in their nice little hotel and take care of you, no matter where you. I went through Europe, it didn't cost me a penny. But anyway, so this is a picture of single-wall nanotubes that are just grown from catalyst. And you can see I can grow them in the pores of the aluminum membrane. The membrane can be very thick. So I can grow 5-micron long nanotubes and all kinds of things. Without these SEM and TEM and AFM and all that, we would be blind to the nano world. So luckily for us, that these things exist. Guess what? Nanocellulose. Cellulose is your paper you're writing on in your book and everything. So, but we want nanosellulose. Why? Well, it turns out nanocellulose has incredible properties. I have a sample at home. Again, I forgot to bring, just using my mouse. I've got a material that is hard, you cannot break it. And they're using it for bulletproof vests. Again, the same reason, when it forms in more of a crystal, not like this, so more crystalline, it's more like a spiral. What happens that when a ballistic material comes and hits that, it disperses the energy. Okay? So the spirals manage to disperse the energy. And by the way, if you're into computer simulation, and by the way, if you want to start a company, from my experience, we need people that know how to simulate materials. They're in demand everywhere. I try many times, oh, I'm so busy. Good heavens, get it. I was telling Dr. Puchai about programs like ComSol and Material Studio right now, where you can start with quantum mechanical input parameters, and you can say, I want to cover this tabletop with something, they'll tell you what to cover it with. It's phenomenal. So ComSol Multiphysics, that's COMSOL Multiphysics. Check them out on the website. And then Material Studio. Those two programs, I have ComSol, but I need someone to program it. So ComSol is just a differential equation solver, and it does basically finite element analysis. And by the way, you know what? You know who one of the pioneers of finite element analysis was? Anybody know? You know. Anybody know who was a pioneer? You know finite element, right? You've heard of that? Finite element analysis. Okay, you'll get it eventually. Basically, it takes an element and models the material around it. It's the simplest way to put it. But I can model everything, any kind of material. It's your own Professor Orsak, your director of this program. He went to UC Berkeley, and he pioneered finite element analysis, computer analysis. Amazing guy, and we're very lucky to have him. Okay, so bacteria can make nanocellulose, And that is so much better than if I make it in sulfuric acid and grinding and God knows what else I have to do. So here we have bacteria that can make it. This is a combination of biotechnology and nanotechnology. Phenomenal materials. We had one student at AIT do a study. They just added nanocellulose to asphalt for the road. They found out it was 30 times better than regular road. Only problem is it's expensive. They may be chemically modified it to bond to the asphalt chemicals and the oily kind of materials. And then once that happened, it became incredibly strong. They're making artificial arms and prosthetics and all kinds of things out of nanocellulose right now. Again, a huge, huge thing. Quantum dots. These are all the same quantum dot, except for one thing. What is a four-letter word? A nice four-letter word. Starts with an S. The difference is only in what? S. Second letter I. Third letter Z. Fourth letter E. Size. They're only different in size. That's it. But look, I can create every single color. Why is this important? They're using this as markers to find cancer in the body, for example. So again, they have these you may have a nanoparticle delivery, and you have homing proteins on it. Homing protein is one that will go to cancer, right? And then you put this dye molecule, which is a quantum dot, on it. Then you illuminate it, and it glows up, and you say, oh, there's the cancer right there. This is very important in oral cancer, because the surgeon, when he removes the cancer, doesn't know if he removed everything. So they sprinkle this stuff in there and then light it up. Oh, I got to take there a little more. Phenomenal. So why is this happening? Well, semiconductors have a band gap. Yeah? You guys familiar with band gap? See, I know you guys are just out of high school, right? Everybody? So I know you don't know. But the band gap is simply metals have no band gap, so they can electricity very easily. But semiconductors have a band gap, so electrons have to jump into it. Okay, and that makes a difference in terms of conductivity. It's called semiconductivity. Here we have different band gap differences. The higher the band gap, more energy is required for the electron to jump. That would be the ultraviolet color. The lower the band gap is the infrared. The red color is longer wavelength, lower energy, so it doesn't have such a big band gap. This is all absolute nanotechnology. Here we go. So the flower petal. So you can do flowers or roses. Either way, you have to explain on your date, okay? That this is why they're fresh. Why flowers are fresh. You can see these little mountains. And this is, the flower petal and the rose petal are very similar. Now, what you see here are grooves, okay? These are micron dimensions, maybe even 5, 6, 7 microns from here to here, okay? At the top, you see the grooves. So what's going to happen? Two things. One, these grooves are hydrophilic. In other words, they like water, all right? But by lowering the surface energy, remember, if I take the energy, if I do this area, I get this by this, right? But if I only take the area of these, my area is almost nothing, right? That means there's not enough energy from these structures to overcome the surface tension of water. But what these things do is they hold the water. They trap the water on the surface, so they keep it fresh. So use this. This is an incredible arsenal in your dating future. Okay, so this is, again, a scanning electron microscope image of the surface of a rose petal. Here we go with the lotus leaf. You can see the water is almost perfectly spherical. And they slide around like this. You can't hardly keep them up on the surface. Here's some more pictures. Different kinds of plants have different kinds of surfaces. I didn't label which one's which one. I think that's the lotus leaf over there. Some of them, now the lotus leaf doesn't have any hydrophilic. These are hydrophilic, but these are hydrophobic. In other words, oily. So they want water to go off. We wrote one paper where we made both kinds of surfaces in one chemical bath. We called it the rose petal and the lotus effect. We made it in one pot. So we did it with zinc oxide nanorods. And depending on the size of the nanorods, we got different. So anyway, it's just absolutely, you look at nature, you see these plants outside, but then you look at it with a microscope, and even better, scanning electron microscope, and you see, oh my God, this is amazing. Metal organic frameworks, you talk about internal collective surface area per gram. They've set records of 10,000 square meters per gram, and that's like unbelievable. That's crazy. But it's basically air. But these chambers are internal surface area. These is a very hot topic right now. Okay, now let's go to 3. Yeah. Oh, I don't want this. I want a little thing like that. Okay. All right, let's move on. Okay, we'll just have a little relax and sit back. Okay, we already know nanoscale components in your body. Life is based on nanomaterials, I think. Life would not work without nanomaterials. Lotus leaf, rose petal, you know the little gecko? You tie toucan. Oh, really? Gecko can stick to the ceiling. How? You know? How does it stick? How does it stick to glass? Okay, its feet have nanostructure. The answer is nanostructure. The color of the butterfly. Enzymes, cell membranes, DNA. Pitcher plant surface, different from the lotus leaf. The pitcher plant is made to be very slippery so that insects will fall into it. So again, that's a nanostructured surface. This is a gecko's foot. Look at that. It has little hairs all over its foot. And that's not even all of it, because if you look at the head itself, it's got more hairs, more little diversions. So here's the gecko. That's his foot. Then at 75 microns, it looks like that. They make it even smaller. This is 5 microns. And you can see the end of it is even more finely divided. And then even that is more finely. That's 1 micron scale. So these things are 100 nanometers, 50 nanometers. That's more than just hair. That's extremely finely divided. You can see all these little structures. Well, it turns out there's a force called the Van der Waals force. How many here have had chemistry? One, nobody? Just nobody? What's your name? What is your name? Kunchu Anaka. Say louder. Sarita. Nice to meet you. But Van der Waals forces are the weakest forces. When I put my hand here, there's Van der Waals forces holding to the cable. I can remove my hand very easily. But if I have gecko's foot, I won't be able to move my hand. Unless I go like this. That's how it releases itself. That's nanostructured material. And guess what? It's a huge industry. You see, I can put up a picture on a wall without having to do a hook and all that. You just put this stuff on the wall, and then they just glue the wall, and then they can remove it easy. But it's not going to fall down. A lot of industry here already on these kind of advanced surfaces. So the gecko's foot is just one example. This butterfly I saw in Costa Rica in Central America. It's called a morpho. And it's like this big, it's huge, huge butterfly. And we were just in the camp, and 2 of them flew right in front of me, right in the sunshine. Of course, I never had my camera ready, never. So no one believes me. But this butterfly is just phenomenal when it's lit up. If there's no light, it looks brown. So what is it about this color? It's called nanophotonic color. In other words, color of the butterfly is due to the nanostructure in its wing. And obviously, blue is favored over every other color. So it eliminates all the other colors, but allows the blue to be. And this is called interference color. Very much the same principle as a soap bubble. So depending on the thickness of these nanostructures and their placement, you can make any color you want. The wing is also self-cleaning. In other words, if it gets wet, the water will roll off. Therefore, if a butterfly is caught in a rainstorm, if its wings absorb water, it would crash to the ground and be eaten by some gecko, right? However, it can fly in water and then find a safe place. But anyway, the water can roll down, and again, here are these nanostructures, right? What do? They reduce the surface energy, which in turn allows water to just remain in a spherical configuration, and it rolls off. There's also self-cleaning. As it's rolling off, it picks up all the dirt. So the butterfly has 2 advantages. It's self-cleaning, it's hydrophobic, which means it repels water, plus its beautiful blue color. Here, TEM. There's an optical microscope, and then a scanning electron microscope. You can see these grooves. And then finally, you take a cross-section of that, and you have a transmission electron microscope. And this is the structure. This is the natural structure. The wing of a butterfly. You go, God, that's amazing. I can't help but look at it and just say, it's made out of protein, like keratin, which is the same as your skin. And look at it. This is the cross-section of that. That's what makes the butterfly blue. the light comes in, it's reflected back and forth, and only the blue color emerges.
Yeah, that is true. Atomic force.
Yeah.
Can you compare contrast the use of that versus electron microscope?
Yeah, electron microscope. Well, that's a good question. Atomic force microscope is very good for the top. Or if you manage to cut it and turn it sideways, it can look at that. So it can also look at this. What the atomic force microscope it does, it's a mechanical object, mechanical device. So it has, it's just like a record player. Do you remember no, you don't. The old record players, they were cut out of wax and they had a stylus that would, as the record went around, it would vibrate depending on what's underneath it. That made the sound. It's the same principle. There's a stylus that's contacting the surface or just barely above it, okay, because there's van der Waals forces pushing. And for the aluminum oxide, it'll go like this, and it goes into the hole, goes like this, goes into, and it makes a two-dimensional image. Actually, three. You can measure the intensity as it goes this way. Transmission electron microscope is an electron wave device. So the wave of the electron is very, very like less than a nanometer, and it looks at objects that way. Just like we can't see this, but the electron microscope can. To see something at the nanometer scale, you need nanometer wavelength. As far as which one is better, this is what biologists prefer, but they also use atomic force microscope. I've never seen, actually, when you see things like this, you always see TEM. So you don't see AFM or STM so much. But those are used mostly in physics and chemistry. But as far as the resolution, this is fantastic. Huh? So I hope that helps a little. Peacock feathers. I told my wife I want to get a peacock. She threw me out of the house because the peacock would make huge noise, and neighbors would come after me. But she likes her chickens. She goes crazy about her chickens. So. But this is a peacock, and his colors are due to, and what's the answer? The color is due to nanostructure. That's the answer to everything. Yeah, okay. Nanostructure. It's nanostructure. The feather has diversions and deviations until you get to the nanoscale. And then these colors. Even the black, I saw black birds out here, some crows. They have luminescence to their feathers. In other words, at certain angles it looks purple, it looks green. That's nanostructured feathers. The dinosaurs had feathers, you know. The abalone shell, the parrotfish. Parrotfish has two kinds of nanotechnology. One is its teeth. The parrotfish can chomp on coral. Everyone knows what coral is, yeah? I brought some coral. I need somebody to test. I want you to chomp on it. See if it breaks your teeth, yeah? It will break your teeth, all right? But the parrotfish, no problem. It can crush the coral and eat the little guys. So why? Okay, why is the teeth so strong? DNA bomb. Nanostructure. Sorry, nanostructure. Nanostructure. It's got much smaller hydroxyapatite crystals than we do. And because it's smaller like that, it's stronger. The moth antenna. Guys, if you're dating, this is another good one, okay? The male moth can detect the female moth by antenna. It can detect one molecule. It's called a pheromone. It's like perfume, yeah? Perfume is like a pheromone. You go crazy. So this is the same thing for the moth. So it follows the signal until it finds the female. But the moth, the structure, the reason it can detect One molecule. Why? Nanostructure. It's nanostructure. And you know what? Today's detectors are studying the makeup of the sensor for the moth. That's amazing. Even the moth at night can navigate by the moonlight, but it has to be anti-reflective. Why? Because if it is reflective, it's going to be eaten alive. So it has nanostructure on its eyes, little things like this, little hemispheres covering its eyes, which are anti-reflective. Thousands of examples. I wish we had more time. We need a whole semester. Okay, abalone shell also, interference colors, layers and very thin layers to make the beautiful shell colors. This is a microtubule in your body. And this is a little guy called kinesin. Now, please look, I want you to play a video. You for kinesin, did you see the little guy walking on the microtubule? That to me is the weirdest thing. Don't you think? I mean, how in the world how did that ever happen? You know, we wonder. But the kinesin takes things away from the nucleus. And there's others that bring it back, myosin and others. But it has little feet and little arms. It's actually a lot taller than this picture. But it takes step. Every one of these is a step. And as far as I'm concerned, it's the most incredible phenomenon I've ever seen. Especially the one about the DNA, how the DNA is replicated and all that. It's all because of these guys. Little nano machine. This is it's called a little protein motor. That's what it is. It's a protein motor. Can we do something in the future with this kind of motor? The motors that they're going to make for your body are not going to be made out of metal. They're not going to be robots. Okay? They're not going to be robots. They're going to be these kinds of protein machines. The DNA, of course, you can see. Again, so here you have DNA. What is it about information? It can do information. It's a computer. It tells you when you need a certain protein, when you need an enzyme, and it codes for it. There's a degenerate code that codes for all the proteins. There's amino acids, which are about 20 or so amino acids. These amino acids are coming together to form the proteins, which is basically everything we are. Of course, there's carbohydrates and lipids and other things too, but mainly protein. So this is some kind of incredible memory computing system that is constantly evolving. And it's about 2.2 nanometers and can be very long. We saw that already. Photosynthesis, phenomenal, again, a phenomenon. The most amazing, again, another most amazing phenomenon is the cell membranes are all 5-6 nanometers. Why are they so thin? Well, because things have to get in and out, in and out, in and out. You have enzymes. You have all the substrates coming, photosystem 1, photosystem 2. And it's all about electrons basically in the form of hydrogen ions that are being transferred constantly. That's what makes it work. We're trying to make solar cells based on photosynthesis model. Okay, another thing is in your small intestine in your body, you have what are called microvilli. And these are what their main function is to increase. Their main function is to absorb. So their function is to absorb the food you eat. The food is broken down in your stomach by enzymes, which are nanoscale. And then once they go into your small intestine, these structures are there to absorb amino acids, sugars, whatever else gets absorbed. And you can see these look like fingers. What is the purpose of them? Is to increase the surface area. That's their only purpose. Absorption and to maximize the absorption. And again, if I take all of these things and lay them flat, again, we have about a tennis court in size of total area of absorption. Tennis court is pretty big. But these things all have other microstructures. Even on them, they have more nanoscale. Look at that, aren't they just, this is a TEM. Again, TEM in biology is weird. But you can see this is a maximizing collective surface area for absorption. The tendons in your body, many layers of structure, all the way down to the nanoscale. Am I being boring? Please, I'm sorry. But everything is nanoscale. It's down to the nanoscale that these tendons, which is why they have the tensile strength of steel. Very strong materials. All the way you can see the different layers of the tendon. The cell membrane, of course, we mentioned earlier. This is a top view of a cell membrane. These are all these are actually molecules, okay? You can see the little round things on the top. I think this is the top view. And less than 1 nanometer across. And the cell membrane cannot be too thick. It's too thick. We can't have diffusion, nutrients cannot flow in and out. Things like that. It just has to be nanoscale. The other experiments of nature didn't work. They failed. Sorry. They failed. So this is what worked. Optimize about a 10 nanometer membrane. And they're reinforced with microtubules and other kinds of protein structures. This is the endoplasmic reticulum. That's the site of protein synthesis. Why is it? Well, again, what is the advantage? Surface area. I go like this, I have a lot of surface area. I have more surface area than just this. This is a mitochondria. That's where all your energy takes place. Energy function takes place. The structures inside the cristae increase the surface area. Very simple thing. The mitochondria is several microns in length. It's a kind of a bigger structure, but inside, a lot of membranes to do what? To make energy. This is a fungus. And you see a lot of surface area. There's more pictures of microvilli. Nature is nanotechnology. Enzymes. To learn when to do that. 2 to 20 nanometers in size. I like to just beat the drum, repeat over and over. Carbohydrate, this is again a picture of an enzyme. Coenzyme comes in there, then the substrate comes in there, and then something happens and the bond is broken. A bond that would never break outside the enzymes because they're very strong. Chemical bonds are very strong. But enzymes can do that. Well, great. Sure, let's take a break.
Before we go into the question, perhaps one question is, I guess if you start from material science and keep going down, you go to nano level. Also, if you start with cellular biology, you keep going down, you go down to nano level.
Good point. I like that.
Is that is there a course or anything university level teaching program that you're aware of that basically gets students to the nano level understanding, agnostic of whether or not it is biological or
There's a lot of programs across the world. Every country has universities that have nano programs. Our approach when we were at AIT was to teach nanotechnology as an independent course. We didn't worry about other things so much like we do here. Here it's more integrated. We're more integrating the picture with biology. We didn't do that earlier. So of course, I think like what you're talking about would be actually quite unique. It would be great to maybe create upper division course with that philosophy here. That would be, and you can do it for different fields of study.
Another question, perhaps. Students here, they try to sort of like bootstrap their understanding of technology to maybe solution or innovation. But a lot of it is a limitation. They can get access to apps programming. So that's something that's a little bit within their reach. But if they want to get into the game of nanotechnology, is it really feasible? Is it something that's viable for a startup or for a small scale player in the nano game, or just exclusively the domain of large research institutions?
I honestly think there's room. Like I have a need right now. Somebody to create images of nanomaterials. None of them are good in the entire lexicon of computer program that I've seen. Someone start a little startup right now. Just start it. What do you have to do in Thailand? Just open a bank account and it's very easy. Get yourself a good computer and start learning basic crystallography. Is very easy. I'll show you that. I'm going to teach you that tomorrow. And then learn how to draw these structures. That would be a great start. I'll buy them from you. I guarantee we'll buy them. I'm writing a book, by the way. I have some books out, very popular. Introduction to Nanoscience, Fundamentals of Nanotechnology. They've been around for a long time. And I'm now doing second edition. All right. So I don't like the pictures I draw. You'll see them tomorrow. They're so terrible. But I want to put some good, I'm drawing them like atom by atom. I said, okay, and I'm using PowerPoint to draw them, please. Don't kill me. We don't have to worry about atomic strength or hydrophobic, hydrophilic, nothing. Give me a good picture. Now, if you have a good program, now there are some programs that can do that. Study them, see what you can do. But I can't find them. I search, I look for pictures and they're terrible. I've got at least 30 different kinds of nanomaterials I want good pictures of. Okay, and how can you do that with all the technology available today? You don't need to be a nanotechnologist. You can do it right now. Right? So if you guys, a couple of you get together and form a little company, call it some nano something, that would be great. Get your LLC, whatever it's called, limited, whatever, and start drawing pictures of, I'll tell you what I need drawn. Learn how to just draw those pictures. There are, for example, there are models of crystallography. And crystallography is just the crystal structure of any material, right? And you can rotate 3 dimensions, this plane and that plane, and different kinds of. Also, I tell you, there's a lot of algebraic topology that has. I'll show you the paper that has modeled them, and you're going to say, that's terrible. How can we make a better one than that? You'll see tomorrow. So algebraic topology is simply equations that we use to model gold 55 clusters. Okay? Just make a good picture. That would be a great start for a business. And as you go through your college education, after 4 years program, right? By the time you're done with 4 years, you'll be pretty much an expert. And these are pedagogical tools. These are for teaching. Now for research, you can then incorporate different aspects of input parameters like bonding strength and things like that. But that's another story. Anyone? Okay. I'm relying on you guys to come through. I have a deadline at the end of the year, so you have some time. Think about it. Form it now. Call it nano or something. Work with Mr. Punjay, just do, do it. Don't waste another second. Do it now. Okay, break.